This review contains some required derivations. I call it required derivations number 6. Basically, it talks about all things gravitational. You see here the gravitational force, the universal gravitational force G times the mass times the other mass divided by the distance between their centers squared. This is an experimental result from Cavendish. This is the universal gravitational constant G, 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. If we use this in our expression to determine the amount of work required for the gravitational force to bring in a small mass from infinity to a position r away from a large mass, then of course the force changes as a function of r, and so we have to do the integral version from our equation of greatness here. When you substitute in the gravitational force law for the f of r and apply the limits of integration from infinity to a distance r away, you see here infinity to distance r, and follow through with the integral, then you get a result for the gravitational potential energy, which is equal to minus g times the mass times the other mass divided by r. This is a negative with the maximum value being 0 at infinity. So it is a graph that one needs to get used to. You can see as we look at an object on the surface of the earth and we lift it up to a distance height h above the earth, that the gravitational potential energy does grow from about there to about there. One particularly interesting phenomenon is to determine the escape velocity from a planet or some sort of gravitational object out in space. So we have a person here that is going to jump off of this planet. Obviously the scale is not to scale. The person will jump with an escape velocity such that when they get to infinity, they won't have any energy left. They won't be moving at all. So that would be the minimum escape velocity required to escape the gravitational confines of the planet. So we simply calculate the total energy at jump, which would be the person's gravitational potential energy plus their kinetic energy. We set that equal to the kinetic energy 0 plus the gravitational energy, which we determined to be 0 at infinity. And so we're able to determine that the escape velocity is equal to the square root of 2 times g times the mass of the Earth or the planet divided by the radius of the Earth or the planet. When a planet is orbiting another object with a lot of mass, say a satellite orbiting the Earth, then we can apply our understanding of the circular motion mv squared over r, which is the net inward force, which must be the gravitational force gmm over r squared. And from that, we can determine the orbital velocity is equal to the square root of g times the mass of the Earth or the planet divided by its radius. Of course, for objects going in circular paths, the orbital speed or the tangential speed is equal to the circumference divided by the period. And so, since we have an expression for the orbital velocity or the tangential velocity from our F equals ma analysis, and we understand that it's also equal to the circumference over the period, then we can set 2 pi r over t equal to the square root of g times mass of the Earth over its radius, and solve for the period. And when we get the period from that expression, we get that it's equal to a gigantic constant times r to the 3/2. This leads to a discussion of Kepler's 3 laws, and here they are listed in red. The first law, there's no particular order, are that orbits are ellipses with the planet or the sun at one of the focal points. The second law being that the planet in its orbit will sweep out equal area in equal times. And the third, Kepler's law, says that the period goes like the radius or its average orbital distance raised to 3/2. One more interesting aspect of uniform circular motion and gravitation is that if we calculate the total energy of the orbit, then the total energy would be the kinetic energy, 1/2 m times the velocity of the orbit, squared, added to the gravitational potential energy, which is a negative gmm over r. And knowing that the orbital velocity squared is just equal to g times m over r, we can then get an expression for the total energy, which is just equal to half the gravitational energy. That is just for uniform circular orbits. The more general type of orbit is an elliptical orbit, and the elliptical orbit, spelled incorrectly here, it should be 2 L's, has an object traveling around, a satellite traveling around a planet, let's say, in an elliptical path where its distance of closest approach is going to have the greatest orbital velocity and the smallest gravitational energy, and its distance of furthest approach is going to have its smallest orbital velocity and its greatest gravitational potential energy. So we can, of course, at any point on this orbit, equate the total energy to some known value. Here I have in green the energy, the total energy of the object, the satellite, at furthest distance, and so here is its kinetic energy, and here is its gravitational energy. And then, of course, that must be equal to the total energy when the object is at closest distance, which again is its kinetic energy plus its gravitational energy. Of course, with elliptical orbits, we can also equate the angular momentum at any time on the orbit to any other time on the orbit, as long as we calculate angular momenta about the planet that's being orbited. Because the gravitational force is always going to be perpendicular to the orbital velocity at any point on the orbit, then there is no net torque. And so the angular momentum is conserved. Actually, the reason is that the gravitational force and the lever arm are anti-parallel or parallel, and that is the reason why there is no torque. So usually in these instances, we are able to equate the angular momentum at the furthest distance away from the planet to the angular momentum at the closest distance. Treating these satellites as point masses, we can simply calculate the angular momentum as r cross p. R and p are perpendicular at closest and furthest distance away, and so we simply get a relationship that says r furthest times mass of the planet orbiting times the orbital velocity at the furthest is equal to a like statement for the closest approach. And of course, looking at the conservation of energy and the conservation of angular momentum sets up two equations with two unknowns, which is very helpful in many cases.